Hi everyone, my name is Claire Tomlin and I'm a professor of electrical engineering and computer sciences at Berkeley. And this is the 14th module in a series that we're recording to support the course EE221A, which is linear system theory at Berkeley. This module is following on from the previous module in which we presented the fundamental theorem, or the existence and uniqueness theorem of solutions to ordinary differential equations. In this module, we're going to be talking particularly about uniqueness. And so we're going to call this module the Bellman Gronwall Lemma, because that's really what we'll talk about today. It's a tool that we use, it's a lemma that we use to prove uniqueness of functions, where we have some idea that those functions are solutions to differential equations. But the Bellman Gronwall Lemma says something more general than that. So let's recall the setting that we're working within. We're working within the study of a differential equation, an ordinary differential equation. And so as we presented in the 13th module, we will go back to that format. Here's our differential equation with some initial condition. X here is a vector. X at a particular point in time is a vector in Rn. F is, so x dot is also a vector in Rn. F is a vector valued function. So f is a function which takes Rn cross R plus, time lies in R plus, over to Rn. And what we did last day was we presented the theorem, which states the following, that if this function f is Lipschitz continuous in x and piecewise continuous in time, then there exists a unique solution to that differential equation with that initial condition, which satisfies that solution is a function of time, which satisfies this differential equation. It satisfies it, what we say is almost everywhere. It satisfies it everywhere that the function is that f is a continuous function of time. Remember, f only has to be piecewise continuous. So there's possible points of discontinuity of f as a function of time. And at those points, the derivative doesn't exist. But that's okay. We still allow that function of time to be to satisfy this differential equation almost everywhere, except at those points of discontinuity of f as a function of time. I'd like to spend a few minutes talking about the machinery. We didn't prove this last day, and we're not going to prove it. But we are discussing some of the machinery used in the proof. We talked last day, well, we talked quite a bit about Lipschitz continuity, and we talked about how you might prove that a function is Lipschitz continuous by using a norm of the Jacobian of f. Today we're going to talk about part of the machinery used to prove uniqueness of the solutions to that differential equation. And we're going to do that because that machinery is useful in itself. And the machinery itself is called the Bellman Gronwall Lemma. Okay, so let's state the Bellman Gronwall lemma. It's a nice little lemma, which is easy to state and easy to prove. So suppose we had functions u and k. These are real valued functions. They're piecewise continuous, and they're positive. They're greater than 0. So real valued, piecewise continuous, and they're greater than 0 on R plus. Okay, so they're going to be functions, let's say, of time, real valued, piecewise continuous, and positive on R plus. And then we also have some constant c, let's call it c1, which is greater than 0. And we'll also have some initial time, and we'll assume that time is greater than or equal to 0. Then the Bellman Gronwall lemma states the following. If u, the function u of time, can be bounded to be less than or equal to c1 plus, actually c1 should be greater than or equal to 0, sorry. c1 can be 0 if you want. So if u of t is less than or equal to c1 plus the integral from t0 to t of k of tau, u of tau, d tau, these are these functions here. Let's just write the k's the same way. Then the following bound can be made. So if you can establish this bound on U, then the Bellman Gronwall lemma states the following, that U of t is bounded to be less than or equal to C1 e to the t0, e to the integral from t0 to t of k of tau d tau. So in the first inequality, the function u appears on both sides. In the second inequality, u just appears on the left-hand side, and that's often a more useful bound to have when you're trying to show uniqueness of functions, and we'll see why when we apply this. Okay, so basically the setup of Bellman-Gronwall says that if you have such a structure of functions and constants, if you can be bounded by this inequality, then you can show that it can be bounded by this inequality. The proof of this is quite nice. Let's just quickly show the proof. So we'll keep the general statement of Bellman-Gronwall down there, and we'll prove it up here. Okay, so let's prove it. Let's just assume, although we don't really have to, that t is greater than or equal to t0. So this is a forwards integration, which is what we typically do. And to make things easy, let's define a capital U of t, which is equal to this, the bound on little u of t. So capital U of t is C1 plus the integral from t0 to t of k of tau, u of tau d tau. And so basically we've just renamed the right-hand side of that inequality. So that tells us that just by that rename that u of t is less than or equal to capital U of t. Okay, so now let's take that inequality and multiply both sides of that by a non-negative function. So take that inequality, multiply both sides of it by this function, which is k of t e to the minus integral from t0 to t of k of tau d tau. So this is non-negative because k is and that exponential is. So if you multiply both sides of that inequality by a non-negative function, the inequality will be maintained. And so we end up with the following, that u of t, k of t, e to the minus integral from t0 to t of k of tau d tau is less than or equal to capital U of t, k of t, e to the minus integral from t0 to t of k of tau d tau. Okay, so let's bring this onto the other side of the inequality and recognize that that expression on the left-hand side is just the derivative of another function. So what we end up with is that d by dt, what we have up here is the same as saying d by dt of u of t e to the minus integral from t0 to t of k of tau d tau. The derivative of that is less than or equal to 0. So I've just rewritten that inequality as the derivative of this function. And now I can integrate that function between t0 and t and get the following. So I note that evaluated at t0, capital U of t0, just from my definition, is just equal to C1. And so we end up with integrating this derivative between t0 and t, and following the rules of integrating that derivative and establishing those bounds, is that little u of t is less than or equal to capital U of t, which is less than or equal to C1 e to the t 0 t1. So the negative disappears as I've brought it onto the other side of the equation in that integration, k of tau d tau, which establishes the bound that we need, that u of t is less than or equal to this bound. Okay, so that's the That's the statement and proof of the Bellman Gronwall lemma. It's nice to know how it's proved because we end up using this in many different places. In the statement of the existence and uniqueness theorem of differential equations, we use it to prove that once you've derived a solution and once you've shown that a function is a solution to that differential equation, that there can be no other solution. And so let's just show that, because I think that is useful. And it allows us to think more generally about how we might use this Bellman Gronwall lemma in other places. So the use of Bellman Gronwall in the proof of uniqueness of solutions to differential equations. So you've got your differential equation, x dot is equal to f of xt. You've got your initial condition, x of t0 is equal to x0. And you've derived a solution, which is this function phi of t. So you've shown that phi of t satisfies the differential equation and the initial condition. So how do you know there's no other function? Well, the typical way to show uniqueness of a function is to prove it by assuming that that it's not unique and then deriving a contradiction. So we typically prove uniqueness style proofs by contradiction. So the question is it unique? You've got a solution, but is it unique? So we assume not. Therefore, there exists another solution, let's call it phi of t, which satisfies the differential equation and the initial condition. So we've got these two solutions and they're not equal to each other. All right, so now it's up to us to try to derive a contradiction. And so now it's fairly straightforward. So we've got another solution, and we know that phi dot is equal to f of phi t, and we know that psi dot is equal to f of psi t. They both satisfy the differential equation, and they both satisfy the initial condition. So phi of t0 is x0, and psi of t0 is also equal to x0. Well, what does that mean? Well, I can write these differential equations in terms of their integral form. So I can write phi of t to be equal to x0 plus the integral from t0 to t of f of phi t, or tau, d tau. And I can do the same thing for my other candidate, or my other solution. Psi is equal to x0 plus the integral from t0 to t f of psi tau d tau. Okay, and these are functions of time too. I've just dropped the t there. Let's take the difference between those two. So I see then that phi of t minus psi of t. I'm going to take the difference and then I'm going to take the norm of both sides. So I'll do a couple of steps in one. I'm subtracting this equation from that equation. The x-zeros cancel, and I can bring the f's under that integral sign since the integration is a linear operator. I'm going to take the norm of both sides, and then I'm going to bring the norm inside the integral. So I end up with the following inequality, that this is less than or equal to the integral from t0 to t of f of phi of tau minus f of psi of tau d tau. Okay, and now I'm going to do one more thing. I'm going to use the fact that f is Lipschitz continuous in this argument here. So f, we know, is Lipschitz continuous in x. So it's Lipschitz continuous in phi and psi. And I can look at the difference between f of phi and f of psi, that norm, and bound it to be less than some Lipschitz function k of t times the distance between phi and psi. And that k of t is a piecewise continuous function which exists between the time interval that I'm interested in particular between t0 and t. And it's a piecewise continuous function in time, so it has a largest value. It has a supremum over that interval from t0 to t, let's call the supremum of that function k of t over that time interval, let's call it k bar. So k of t is less than or equal to k bar over times between t0 and t1 or t0 and t, whatever interval we're looking at. And so then I can bring that k bar outside the integral and rewrite. So I've used Lipschitz continuity to rewrite f, or to bound f, to be less than or equal to k of t times this norm here. And then I'm calling k bar the largest value that k of t takes on in that integral. So it loses its dependence on time. You can bring it outside the integral and establish the following inequality. Okay, but that's nice because now this inequality here is in the form of the hypothesis of the Bellman Gronwall lemma. Namely, if we call this the function u of t in the Bellman Gronwall lemma, if we call this k bar the function k of t, it doesn't depend on t here, and that's fine, but if we call that function k bar the k of t in the Bellman Gronwall lemma, and then we see that integral of that same term u of t here, and the constant c1 is equal to 0. Okay, so the u of t and the k of t and the c1 are the terms that we used in the Bellman Gronwall lemma. So we've proven the Bellman Gronwall lemma, namely that if we can establish u of t to be less than or equal to c1, which is 0 here, plus k of t, or in the case of the Bellman Gronwall lemma, k of t was under the integral sign, so that doesn't matter here. But we've got this term on the right-hand side that depends on the integral of u of t. Then the Bellman Gronwall lemma says that we can replace that right-hand side. We can further bound u of t by this inequality here. And what does that mean in this case? It just means that, let's just erase this part here so we still see the machinery. It means that the distance between, so u of t, which is the distance between phi and psi, is less than or equal to c1, which is 0 in our case here, times e to the t0t, k bar, d tau. Well, this doesn't really matter because of the 0 here. That right-hand side just goes to 0. And we have that the distance between phi and psi has to be less than or equal to 0. But a norm, by its definition, is always greater than or equal to 0. So that tells us that that norm here must be equal to 0. Or we can just replace that right-hand side with 0, the inequality with an equality. For a norm to be equal to 0 means that the thing inside the norm has to be equal to 0, which means that phi must be equal to psi. So we've established the contradiction where we assumed at the beginning that we had two different functions, phi and psi, and then in looking at the development of this, we derived, using the Bellman Gronwall lemma, that indeed phi must be equal to psi. And since these were chosen, well, this was our candidate solution, and this was chosen to be any other solution, it's generally true that any other solution that you find to that differential equation must be equal to any other solution. You can only have one of them. So what we've done here is we've presented part of the machinery which is used to prove the fundamental theorem. In particular, we've shown here the Bellman Gronwall lemma, and we proved it. And then we used it in example to prove uniqueness of solutions to our ordinary differential equation. And what we used in the proof was the Lipschitz continuity of the function f. So you saw that condition come out here in that part of the proof. So we haven't proven the part of the theorem which shows that there exists a solution, but this is the machinery that shows uniqueness of the solution. Good, so we've, in summary now, over the past two modules, we've presented the fundamental theorem, we've discussed what the conditions mean, we've used those conditions, and in particular, we've proven the part about uniqueness of solutions in that, expression of the ordinary differential equation. Now what we're going to do is move on, and in the next several modules you're going to see particular forms of differential equations that we will show satisfy the conditions of the existence and uniqueness theorem, but that also lead us into the general theory of linear systems. Thank you very much.